This lecture will define the R-squared statistic, and I'll compare it with the correlation coefficient that we learned about last time. So what is R-squared? R-squared is a measure of how closely our data fit the regression model. And so this is looking once again at how closely our observations fall to that line. Are they all scattered about, or are they pretty much close to that line? And so it goes between 0 and 1, with 0 meaning that our data are all over the place, that they basically don't fit the regression model at all, and 1 meaning that they are perfectly on the line. And intuitively, R squared is the square of the correlation coefficient, which is also known as R, right? So if this seems familiar, this idea of measuring fit of how variables fit together, it's because it's very related to this correlation coefficient. So in what ways are the R squared and correlation coefficient similar, and how are they different? So let's think about this a little bit more. The R squared, again, is a measure of how closely our data fit the model versus the correlation coefficient, or Pearson's R. And that's a statistic that measures a relationship between two variables. So R squared is how closely the data fit the regression model, or for bivariate regression, the regression line, and correlation coefficient is just about how much they are related to each other. So as we compare these two and think about how we'd use them, let's go through a few questions. So first, does the statistic tell us if the relationship is positive or negative? And with the correlation coefficient, it does. It varies from -1 to +1. And so that tells us that as x goes up, does y go down, right? Is there a positive or negative correlation? R squared doesn't. And just thinking, very basic math, if R squared is the square of R, you are, multiplying, say, a negative number by a negative number, making a positive number. So you can't tell if there was a negative relationship there in the first place. And that's why it varies between 0 and 1. Secondly, do we know which variable is the independent variable and which one is the dependent variable? With the correlation coefficient, no. We just know that they have some sort of relationship. There's no assertion of causality. We don't know which one's an independent variable. We don't know which one's dependent variable. We just know that they go together. Versus R squared is based on the regression model, and regression is about causality. So there we have asserted one of these is the independent variable. One of them is the dependent variable. And then finally, can we use the statistic for analyses of more than two variables? So I'm thinking ahead for when we do multivariate regression. And the correlation coefficient, no, it only works if you have two variables. Versus R squared, which is that as you make your regression equation more complicated, as you add more variables in, you still can talk about how much your data fit that overall regression model. So you can apply the R squared beyond simple two-variate relationships. So I want to add a little bit of caveat here. The R squared is a common statistic that people report on, but there are a lot of limits to it. And I don't want you to think that this is the most important thing to pay attention to in your regression model. So R squared is not the most useful output of regression results, especially once we move into multivariate analysis. So you might see this for a number of reasons. So first of all, you can have other variables that have a bigger effect, but it doesn't mean that our variables aren't important theoretically. So think about this, if you have a relationship between two variables, you might get a low R squared value, because what that means overall is how much is the general variation in your x, how much does that explain variation in y? So imagine that you're looking at whether people vote Republican, right? And you want to look at the effect of serving in the military on voting Republican. So does serving in the military make you more likely to vote for the party that is more associated with aggressive foreign policy? You could imagine that there could be an effect. And you could find that, say that serving in the military makes you 4 times more likely to vote Republican. Well, that's a pretty big size effect. The problem there is that there are a lot of other factors that are going to have a much bigger impact on voting Republican. So, for example, party identification. If you define yourself as being a Republican, that's going to be much more important in whether you vote Republican. The party identification of your parents, for example, also. Party identification of your spouse. These matter a lot more than whether you served in the military in terms of explaining variation in who votes Republican. So compared to these other factors, military service is unlikely to explain much of the variation. It's only going to capture a small portion of variation in whether somebody votes Republican. But you have a big impact, right? So I said that it was multiple times more likely if you serve in the military to vote Republican. If you're just focusing on the R-squared, you're going to lose that impact there. So rather than focusing primarily on R-squared, there are other factors that are more interesting and more important. And this is something that in the Whelan book, they call the 3 S's, and I really like this. So first S is looking at the size of the effect, right? How much does your change in the independent variable lead to a change in your dependent variable? So remember, with the military example, I said that serving the military makes you 3 times more likely to vote Republican. That's a big size of the effect. Next, the sign of the effect. Is it positive or negative? This is basic but really important. Does serving the military make you more or less likely to vote Republican? And finally, statistical significance. Are your results statistically significant? Can we reject the null hypothesis that you're seeing some sort of correlation that's simply due to chance? So how confident are we of that size, the effect that we observed? Can we say that it is beyond 95% likely that there is some relationship in the underlying data and not simply in our sample? So we'll go more into statistical significance and how that applies to regression in future lectures. But just keep this in mind. These are the most important things that you should be thinking about and looking at when you look at a regression table. The size of the effect, the sign, and the level of significance.